Before I talk about meteorites, I want to talk about meteors themselves, that flash of light that you see in the sky. And triangulating on these, it tends to be up in the mesosphere. That's where the atmosphere is getting thick enough that these things are starting to heat up, and make this flash of light burn up, if you will, as they come in back into the atmosphere, or come into the atmosphere. Now, what's going on here? Because people think, well, if it's 50 miles up, it's got to be pretty big in order for you to see it like that. Well, the answer is no, not really. You go out during a meteor shower, and a lot of those little flashes are caused by things about the size of a rice grain or a sand grain hitting the atmosphere. They're just moving really fast. So how are you able to see something that small? And the answer is you don't. What you're actually seeing is the fluorescing gas or the shining gas. What's happening is the solid object here that makes this up is actually a very small thing punching through the atmosphere. As it's punching through the atmosphere, it is compressing the gas ahead of it. That gas is creating a shock wave here through the atmosphere because it's going at hypersonic velocities, not supersonic, but hypersonic, much faster than supersonic. And it's creating a wake here of highly compressed and shocked gas. You're actually ionizing the gas as you're going through here, and then this ionized gas, you're knocking electrons off. The electrons are coming back, and you're seeing not so much the solid object, you're seeing this glow of gas glowing for a fraction of a second behind it as it's reabsorbing the electron. In the process, you're compressing the gas. When you squeeze a gas, it gets superheated, and that heat is being transferred to your meteoroid. And so that's why we sometimes say these things burn up, because the little ones will burn up. Now, the really little ones actually slow down due to friction or the dynamic forces here before they get hot enough to burn up. A little bit bigger ones burn up, and the really big ones, the bigger ones actually make it to the ground. Only the outer parts of them burn up. So, common mistake is to say that our atmosphere protects us by burning up all the stuff coming in. Really, it just burns up the medium small ones. The really big ones still make it through. Okay. The meteor, this flash of light, though, can sometimes transition into something we call a fireball, or that's layman's term. A bolide is the actual astronomical term. So what happens is you have a meteoroid, and the meteoroid is coming into the atmosphere. And as it comes into the atmosphere, it compresses the gas. It gets super hot. But Newton's third law, for every force, there's an equal and opposite force. Pushing forward on this gas, compressing it, pushes back on the meteoroid. And some of these things are not well put together, and so you put a big enough force back on it and it fragments, and so it might break into several smaller things and then dissipate. Each one of those smaller things might break up into even smaller things, and then some of those either slow down and then quit glowing the gas, or they will just burn up. And so as you're looking at it from the ground, you look up and you see this thing flash through and then have an explosion high over your head. You normally don't hear the explosion because it has to get real close to the ground in order for that shock to actually be audible. So normally the explosion is happening many miles over your head. You don't actually see that. You just see you just see this thing come in and break apart in little pieces that fly, in different parts of the sky, and then they all dissipate. But that would be a bolide, or layman's term is a fireball. So here's kind of an example of that. And then sometimes afterwards, you sometimes see a lingering trail from ionized gas that's actually hanging around, and you can actually see it slowly blowing or dissipating due to motion of gases in the mesosphere. Or sometimes, you have a dissipating cloud here left over for where the thing hit. Okay. Now again, sometimes you see these things ahead of time. We talked about this before. In October of 2008, they discovered something that was about to impact the Earth, and it did. It hit over the northern Sudan. And so this was technically a bolide because it did not make it all the way to the ground. It exploded still up in the air. And so that's an example right there. The impact was the equivalent of about 2 kilotons of TNT. That's somewhere, about 1/6 of the Hiroshima bomb. So it gives you an idea as to how big of an explosion that was. It was visible almost from 1,000 miles away and from a satellite. Okay. Things that make it to the ground we call meteorites. The really tiny ones, the dust-sized ones, actually don't make it to the don't burn up. What happens is they hit the atmosphere, and the shock of hitting the atmosphere slows them down before they get hot enough to burn up. And so then they just float down. NASA has a couple of ultra high altitude aircraft. They're actually converted Canberra surveillance planes that are used to fly as very high in the stratosphere, and they collect these dust particles, interstellar dust that's floating down to the ground. You can actually do this on the ground too. You can actually collect interstellar dust. You put something out and collect it. And so one way of doing it is put like a microscope slide out and put something like petroleum jelly across the top of it, so that when dust particles hit it, they will stick. And then you put it under a microscope and study it. And we actually tried that some years ago on campus, and we're a little bit disappointed because all we collected were pollution particles. We didn't actually see any definite micrometeorites. But just over a 24-hour period, each of the slides was completely covered with pollution particles. So just an idea as to how that experiment might work, but it hadn't worked well in the DFW area. Smaller things, several inches across, they burn up. Something somewhat larger than that, basketball sized or medium, softball sized, up to boulder sized, they sometimes don't burn up, depending on which direction they come from, whether they come up behind Earth or in front of Earth, how fast they're moving relative to Earth. Those sometimes make it to the ground and actually hit and make a small crater. And these are some of the ones you find, some of the meteorites you find around. The bigger ones that are like bus size or automobile size, most of them actually do break apart in the atmosphere before they make it to the ground. And they detonate as atomic bomb sized impacts right there. And the really big ones, though, they make it to the ground before they get a chance to break up. The ones that are miles across, they're going to come right through the atmosphere, and they will hit the ground, and they will hit the ground hard. And so those are the ones that make the sizable craters. When you look at the moon, all those craters you see come from the very large ones, the ones that our atmosphere does not protect us against. We've now come to realize that these atomic bomb-sized blasts are far more frequent than we used to think. I have a book in my office that we also got for the library called The Rain of Iron and Ice, and it was an eye-opener for me when I read it some years ago about the meteorite impact and so forth. And the presumption in the book is that once or twice a century that you get an atomic bomb-sized impact. However, we're now realizing that it's far more frequently than that. The atomic bomb-sized impacts are vastly more frequent, probably once or twice per decade, rather than once or twice per century. Sometimes these things make it to the ground. Okay, if they do, they're a meteorite. There was a bolide visible over New York quite a few decades ago, and a chunk of it actually flew through the sky and hit a car. Okay, guy was minding his own business indoors late at night, and then all of a sudden he had a wham out where his car was parked. Walked outside, thought some kids were vandalizing something out there, saw the entire back end of the car cake smashed in, and underneath was a rock. Now here's the interesting thing. the rock was starting to cover itself in frost. Okay, now why would it be covering itself in frost? Well, this meteorite had been in deep space. The interior of the rock was below freezing because it's so cold in space. As it came through the atmosphere, the outer edges of it heated up, but rock is not a very conductor of heat. And so what happened was the outer edges got hot, but the inside was still cold. Slammed into the ground, and by the time it got out there, the ultra cold in the interior had caused frost to start forming on what had been a really hot and charred exterior. By the way, good news and bad news out of all this. First of all, the insurance declined to pay the damage for his car. It was not insured against meteorites. And he did not get to keep the rock. The rock hit the ground. Meteorites are not finders keepers. The rock belonged, he was renting the house, so the rock belonged to the owner of the home, the one who owned the mineral rights to the land. And this sort of thing has happened several times. You had a meteorite a few years ago hit a dental office in North Carolina. The dentist, advertised on TV, hey, come get your teeth cleaned, and I'll let you touch the meteorite. And the next day, the owner of the building came to claim his meteorite and ended up in a court battle, but the law says it belongs to whoever owns the mineral rights, not who finds it. And so, the dentist not get to keep the rock. However, the owner of the car didn't get to keep the rock either. However, a museum paid an exorbitant amount of money for that car to display for a vehicle that was struck by a meteorite.